Okay, so we're going to start talking about fundamental identities this week. And so identities are things that are always true. So for example, 1 equals 1 is a really boring but true identity, okay? For us, our identities that we start with are going to kind of fall into several categories. We're going to have our even and odd identities. We're going to have our reciprocal identities, our quotient identities, and our Pythagorean identities. Now, all three of these, the reciprocal identities, the quotient identities, and the Pythagorean identities, are things we've actually already talked about in class. The new ones are going to be these even and odd identities. We're going to go over all of these in this first video and then look at how we use them to, do stuff with our functions, okay? Okay, so to start with, even and odd identities. So even and odd functions have different types of symmetry. So we're going to start by talking about even functions. And even functions are symmetrical about the y-axis. This is line symmetry. This means if you fold in half along the y-axis, the two halves of the function will match up. And the most kind of common even function, I know this isn't a trig function, but the most common even function is the x squared function. Now you can see the x squared function, if we were to fold in half along the line y equals x, the two halves of the function would meet up, okay? This is a y-axis symmetry, which makes this function even. Now kind of a shortcut for thinking about when a function is even is this little trick right here. So for our function, if plugging in x and negative x gives the same result, then a function is even. And we can see that over here. If I plug in, say, 2 into the squaring function, well, I get 4. If I plug negative 2 into the squaring function, I also get 4. Okay, notice that what that does, it shows us that 2, 4, and negative 2, 4, the points on this function, right, are also reflections across the line y equals x, okay? So positive values over here, positive x values over here, match up to negative x values over here, or f of x equals f of negative x. So that's even functions. Now let's think about odd functions. Odd functions also have symmetry, but it's not line symmetry or mirror symmetry. Odd functions have origin symmetry. And origin symmetry is a type of rotational symmetry. Now, rotational symmetry basically means I can rotate a figure, so spin it, and it will look the same before I've rotated it a full 180 degrees, okay? So let's look at something that has this origin symmetry, this rotational symmetry. A common example is the x cubed function. So if you can imagine, if we were to spin this, if I were to stick a pin right here in the origin and spin my x cubed function, when I spun it 180 degrees, it would look the same as where I started. So let's see if I can do just a quick demo of that. Okay, so looking here, here is our x cubed function, right? And if I spin it, when I go 180 degrees, it looks exactly the same. That's an example of rotational or origin symmetry. Okay, this is symmetrical about the origin through spinning. Okay, so x cubed is an example of something that has origin symmetry or is odd. Okay, and here's our trick for origin symmetry. If plugging in a negative x results in a negative function value, then we have odd symmetry. So let's look at what this looks like. If I plug in 2 to the cubing function, I get 8. Notice that that's not the same thing as if I do if I do negative 2, gosh, I can't type, negative 2 cubed. Instead, these are off by a negative sign. And in terms of our graph, that says that 2, 8, which is up here in our function, right, is going to match up with negative 2, negative 8. I'm sorry, I cannot type at all. Okay. So odd means it has origin symmetry. Now what we want to do is we want to classify our trig functions as even, odd, or neither, because some functions are neither. Let's look at what happens when we do x squared plus x cubed. Okay, this function is neither odd nor even. It's clearly not even. And it's not odd because of this little bump here. Okay, if I spun this 180 degrees, the little bump would come down here, and this does not have origin symmetry. Okay, So again, what we want to do is we want to take our 6 trig functions and decide which are even and which are odd. So let's take a look at that. So let's look at our sine function first. Okay. So our sine function, the easiest one visually, I think, to check is to check for that y-axis symmetry. In other words, is this symmetrical about this line? No, it's clearly not. If I were to fold in half, the 2 halves would not match up. Okay. So now origin symmetry. Origin symmetry we can try and visualize. If I spin this 180 degrees, is that going to look the same? I think it is. But if we really want to check, we can use this. Okay. This says that negative sine, so throwing a negative out in front, negative sine should look the same as sine of negative x. And Desmos shows us that those 2 functions are exactly the same. Okay, so our sine function is odd. We're going to put it under our odd functions. Okay, now let's look at cosine and check cosine. Cosine, oops, turn it on. All right, cosine. So again, let's check for y-axis symmetry first. Well, it sure looks like if I fold in half along the y-axis that this is going to be, these halves are going to match up. So this does seem to have even symmetry, and if I want to double check, even symmetry means that cosine of x is the same thing as cosine of negative x, and Desmos shows that that is certainly true. So cosine of x is even, so I'll move it up here. Now let's check tangent. So let's just look at our tangent function for a minute. Okay. Tangent, what kind of symmetry do we think it has? It clearly doesn't have y-axis symmetry. I can't fold in half along the y-axis and get my 2 halves to match up. Looks like it might have that origin symmetry. I could be able to spin it. In order to check that, we're going to graph negative tangent and compare that to tangent of negative x. And look, those 2 graphs are exactly the same. So tangent also is odd. Now let's look at cotangent. All right, cotangent. So looking at cotangent, what do we think? Well, it's pretty clear that cotangent does not have y-axis symmetry. If I were to fold those in half, they would not match up. So let's look for origin symmetry. I think it's harder to picture origin symmetry, so let's check it using our little cheat here. If this has origin symmetry, the negative cotangent has to equal cotangent of negative x. And look, those 2 do certainly match up. So cotangent is also odd. All right, let's check secant. Okay, secant, so looking at secant, y-axis symmetry. Sure looks like this is gonna be symmetrical over the y-axis, so that makes secant, even. Okay, and then cosecant. Let's check, oops, I didn't mean to delete that. Let's check cosecant. Okay, well, cosecant certainly does not have y-axis symmetry, so it's not going to be even. So let's take a look. Cosecant, looks like if we spin it here, are we going to get the same thing? I think maybe. So let's check by checking negative cosecant. Does that equal cosecant of negative x? And yes, those 2 are equal. So this is also an odd function. Okay, so that's examples of odd and even. So even functions are cosecant and secant. Odd functions are sine, tangent, cotangent, and cosecant. And those are going to make up the start of our fundamental identities. Okay, and in particular, if we kind of look at our kind of a cheat sheet for those fundamental identities, it's going to look something like this. So notice that this doesn't specifically say that, say, cosine is an even function, but it does say that cosine of negative theta equals cosine of theta, which remember was our check for something being even, okay? So these are our even and odd identities, and we're going to use those as we move through and do things like proving or verifying identities, okay? All right, so next we're going to real quickly review reciprocal and quotient identities. All right, so next let's talk about our reciprocal identities. Reciprocal, remember, means flipping numerator and denominator. Okay, so 3/4 reciprocal is 4/3. Now, our reciprocal identities, one way to think about where they come from is from kind of our unit circle or our circle definitions. So if we have an angle in standard position, we're defining x, y, and r, where x is our horizontal distance, y is our vertical distance, and r is our hypotenuse, remember. Then we know that, for example, cosine is x over r, and secant is r over x. Notice that cosine and secant are very closely related. X over r and r over x are reciprocals. That means cosine and secant are also reciprocals. In other words, cosine is equal to 1 over secant, and secant is equal to 1 over cosine. Or this relationship right here. So there's one of our reciprocal identities. Now we have two others, right? So for example, looking at sine and cosecant, sine is y over r, cosecant is r over y. So those again are reciprocals. So our reciprocal identities for sine and cosecant can be described as this. And then finally, tangent and cotangents share that reciprocal identity. Okay. So here are our reciprocal identities. Sine is equal to 1 over cosine, which means cosine is equal to 1 over sine. Okay. All right. So reciprocal identities, relating those two things together. Next, we're going to talk about our quotient identities. So quotient identities specifically refer to tangent and cotangent and how we can think of tangent and cotangent. So let me get those guys ready for us. Okay, so our quotient identities are going to relate tangent and cotangent to sine and cosine. And the way they're going to do that is by looking at these relationships here. So we know that tangent is equal to y over x. We know that sine is equal to y over r and cosine is equal to x over r. Well, with a little bit of algebra, our favorite thing, right? We can see that if we do sine of theta over cosine of theta, well, sine of theta is y over r, and cosine of theta is x over r. So if we remember how we divide fractions, this is y over r divided by x over r. But dividing by fractions means multiplying by the reciprocal, so y over r times r over x. Notice that our r's cancel, and we're just left with y over x. But y over x is the same thing as tangent. Y over x is tangent, so that means we can express tangent as sine over cosine. Similarly, cotangent is the reciprocal, look right up here, cotangent is the reciprocal of tangent, meaning if we flip numerator and denominator, we'll have the quotient identity for cotangent. Oops, I did not write it. I just copied and pasted. Oh well. So cotangent is going to be equal to cosine over sine. So those are our quotient identities. Last, we have our Pythagorean identities. Now remember that we talked about the Pythagorean identities a while ago, okay? And the easiest Pythagorean identity is the sine squared plus cosine squared equals 1. And then we also have the others. So we also have that tangent squared plus 1 equals secant squared, and we have that 1 plus cotangent squared equals cosecant squared. And all of those come directly from our unit circle and obviously the Pythagorean identity. That's why they're called the Pythagorean identities. Okay, sorry, our Pythagorean theorem. Pythagorean identities come from the unit circle and the Pythagorean theorem. Okay, so these are all going to be things that we want to know and use as we're moving forward. Okay, so I'm going to go ahead and pause to put up our Pythagorean identities. Okay, so here are our Pythagorean identities. Sine squared plus cosine squared equals 1. Tangent squared plus 1 equals secant squared, and 1 plus cotangent squared equals cosecant squared. And again, remember, we did this back in class a while ago, but those come directly from manipulating our x over r, y over r identities. So if I were to take sine squared plus cosine squared and rewrite it as y over r squared plus x over r squared, and then do some algebra, I could show that that was equal to 1. Okay, so these make up our fundamental identities: the even-odd identities, the reciprocal identities, the quotient identities, and the Pythagorean identities. You're going to want to become familiar with those because we're going to be using them quite a bit as we continue.